Hello and welcome to Empowered Learning. This video will be about how to find the domain of a function. And for right now, we are sticking with the general functions, algebraic ones. Um, I'm not going to cover anything as far as finding the domain of logarithmic functions or exponential functions. But linear functions, rational functions, nth root functions, whether they are even nth root like square root of something or odd nth root like cube root of something, I will cover in this particular video. For information on how to find the domain of exponential functions or logarithmic functions, um, I have other videos on that, and you can look in my logarithmic and exponential video series to find out that information. Also, if you are looking for information on finding the domain of a composition function, it'll be very similar to what I'm doing here, but there are a few other things that you need to consider. So I would ask you to go to the series I have on composition functions to figure out how to find the domain of those type functions. All right, so now that we've sort of identified what we are going to do and what we're not going to do, um, what I really want to say here is that in finding the domain of a normal algebraic type function is relatively easy. And I say that because there are only two things that we need to look at. The first thing I have outlined here is that we do not want to plug in or evaluate our function that in such a way to where the result is we're dividing by 0. So to give you a quick example of that, let's say if I had a function y equals 1 divided by x plus 3. Okay, so here I know if I were to evaluate this function when x is -3, in other words, y of -3, I would get 1 divided by -3 plus 3, which is the same as 1 divided by 0. And of course, 1 divided by 0 is undefined because we cannot divide something by nothing. And so remember here that whenever we define what a rational number is, which is basically a number that looks like a fraction, um, 0 is not allowed in the denominator. So thus, this is why we say that the domain of this particular function I just came up with will be all the values of x except for -3. And if I was to write that in interval notation form, it would look like this. Okay, and so here all I'm saying is that I'm skipping the number -3 here, and I know that by the parenthesis that I see there. And this union here says that I can pick any number that's in between this, or all the numbers that are in here from -infinity to -3, not including -3, or, because that's what the union means, I can pick anything that's greater than -3, but I can't pick actually -3, okay? So no matter what type of function you're dealing with, if you have a function that is sort of written in fraction form and you have a value or values of x that make the denominator 0, then those values of x cannot be in the domain of that function. And so to be clear, what we mean when we say the domain of a function, we mean the values of x, quote unquote, values of x that are valid for the function. Meaning, if I plug in a value of x for a particular function and I plug in a value that is a real number and I get out a value that is a real number, then that x value that I plugged in is in the domain of the function. Meaning that I had an x value that I plugged in or evaluated for it, and I came out with a corresponding y value that was also a real number. So every x value, if it's in the domain of a function, it will have a corresponding y value that is also a real number. Anytime that we find values of x that are not in the domain of a function is when we plug in or evaluate a function at a particular value of x, and we do not get a real number for the corresponding y value or the output. Okay, so I wanted to make sure that that was clear. So this is the first thing. Make sure that we do not plug in a x value that makes us divide by 0. So for the second thing, we want to make sure that whenever we're dealing with an even nth root here, that we do not want to evaluate or plug in a value of x that will make this type of function have a negative number in under the square root sign or fourth root sign, okay? And I'll give you an example of that. Let's now do y is equal to square root of x plus 3. So in this case, if I were to, let's say, plug in a -5, okay, then of course square root of -5 plus 3 is going to be the same thing as square root of -2. And of course here we know that square root of -2 is not a real number. And we know that because there is no real number that exists that you can multiply times itself twice to get -2. And we know that because with real numbers, we know that anytime we multiply a positive number by another positive number, you get a positive number. And anytime you multiply a negative number by a negative number, you still get a positive number. So here there is no way, according to the rules for real numbers, that the answer to this question here, which is what number do I multiply times itself twice to get -2, is going to exist within the real numbers, okay? So matter of fact, we know that any number that is going to be less than -3 here is going to be a number that can be in the domain. So simply put, and I have this information down here, we say that for any even nth root number, and what I mean by that is any time or any even nth root function. So if I had square root here, or if I changed this and had fourth root, or if it was sixth root, eighth root, 10th root, 12th root, whatever, as long as the index here is even, we know that for this example here, whatever this is going to have to be greater than or equal to 0. And mathematically, what we say is this is non-negative, okay? So in doing this, if we solve this, of course, we will see that x has to be greater than or equal to -3. So values of x that are -3 or higher will be allowed to be plugged into this function here. And values of x that are smaller than -3 will not be, because that will produce a negative number, okay? So that's kind of what this information is saying here. Now, to make sure that this is clear, I am going to come here and say, let's do cube root of x plus 3. In this case, since we have an odd nth root, not an even one, there are no restrictions on odd nth root functions as far as having numbers under the radical here that are negative. And of course, the proper way to say that is that your radicand is negative. So radicand just means the expression under the radical of an nth root function. So if you ever see that word radicand, then you know what that means. And I'll spell that out. So radicand. All right, so in this case, the domain of this function is all real numbers, because with odd nth root functions, we can have negative numbers under the radical. And to give you an example of that, let's say if I took the cube root of -8. Of course, we know the cube root of -8 is -2, because -2 multiplied times itself 3 times will give us -8. So that's just one example of letting you know that for an odd nth root function, we can have negative numbers in the radicand, okay? So now that we've gone over that preview and you sort of see what it is that we're doing here, I'm going to do several examples to kind of show you how we deal with trying to find the domain of these types of functions. And what you're going to see is that in this case of the even nth root function here, being that whatever is in the whatever the radicand is has to be greater than or equal to 0. There will be one exception to that rule, but when we get to it, you'll see why that is. All right, so let's move on to some of the examples here. All right, so before we go to our examples here, again, I want to reiterate that the two things that we are looking for is when do we have a situation to where we have an x value that's going to make us divide by 0, or do we have a situation here, and do we have a situation here to where we're dealing with an even nth root function and the radicand, or the expression under the radical of the even nth root function, is negative. So in this sense, we want to make sure that whatever this denominator is, we make sure that we set it to not being allowed to equal 0. And here in this example, we want to make sure that we keep whatever this expression is to be greater than or equal to 0. And of course, we'll have one exception to that. All right, so in this example here, we ask ourselves these two questions. We know that this is a linear function, so we don't have anything that's going to look like a fraction where we have x in the denominator, because of course if we looked at this like a fraction, it would just be x plus 3 divided by 1. So we don't violate this first restriction here. For the second restriction, we don't have square root or cube root or any even or odd nth root of anything here. So in this sense, there are no restrictions. So that means for every x value that I have that I want to evaluate this function with or plug into it, I'm going to get a corresponding y value out as a result. So in this case, the domain of this function is just going to be all real numbers. Okay, so that means for every x value I have a corresponding y value that goes along with that. Okay. Now, in this example, example B, we have square root of 3 minus 2x. Now, if we come back here, we see that we don't have anything here that looks like a fraction to where we have x in the denominator, so we don't have to worry about violating this rule. But of course, we have this one. Of course, this is square root, so this is like index 2 here. So here we would have to say that 3 minus 2x has to be greater than or equal to 0. And of course, if we solve that, if we add 2x to both sides, we'll get 3 is greater than or equal to 2x, and then divide both sides by 2. And we see that 3 over 2 is greater than or equal to x. Or if we put that another way, reading from left to right, x is less than or equal to 3/2. So that means the domain of our function now, and I'll write it up here, is going to be all values of x. Let's erase that and try that again. It's going to be all values of x that are less than 3/2. And that's how we would write it in interval notation, where the bracket here represents that we can actually include 3/2 or 1.5 as one of the values that's in the domain. Okay, so any value of x that is 1.5 or lower, we can plug in here for x, and we're going to get a result under the radical here that is going to be a number that is non-negative, meaning 0 or higher. If we plug in anything that is higher than 1.5, for instance, like 2, then we'll see that the result of the radicand is going to be a number that is negative, and we know we can't have that. Okay? All right, so let's move on to example C. So example C is an example of a rational function. And in this case, the first thing that we were looking for to see if we're going to violate which is we don't want to plug in anything that makes us divide by 0. We see that that could be violated here. Because of course here, we know that if we plugged in a -2, that would make our whole denominator 0. And if we plugged in a 3 there, that would make our whole denominator 0. So here, to formally write this out, we know that x plus 2 can't be 0, and we know that x minus 3 can't be 0, which in turn means that x can't be equal to -2, and x can't be equal to -3. So when we write the domain of this, we know that the answer is going to be all real numbers except for -2 and 3. All right, so if we write this in interval notation, this will look like the following here. So of course, remember that -2 is smaller than 3. So we're going to start off going from -infinity to -2 and skip that, kind of like how we did here in example, what was it? The earlier examples that I did. And then from there, we go from 2 on to 3, and we skip 3. And just to be clear here, if we were writing this on a number line, it would look like this, to where all the values of x here would be included except for -2 and 3. And so one way that we could do this is kind of do these parentheses here to show that we're skipping -2 and 3, but we include everything else. So looking at that, we'll come here and let's say got all of that. Come here and we want all this inside of here. Okay. So we'll kind of trying to see if I can shade it. Yeah, we'll kind of have it like that. And then we'll have all this in here. And then we'll have all that in there going this way. And so, of course, I'll just go ahead and make this all in black too, so you'll see what it looks like. Now, another way that we could do this is you could also just put circles around here and then just say, all right, we got all these numbers in here, all these numbers in here, and all these numbers going this way. Okay, but either way would work. All right, so let's move on to examples D and E. So examples D and E are a little different than what we've seen before because now we have to consider both of the things that we're looking at as far as the things that we want to make sure that we don't violate. So for example, D, if you notice here, we have square root of x plus 1 in the numerator. So that lets us know that our radicand here, which is x minus 1, that has to be greater than or equal to 0. In addition to that, we also know that our denominator here can't equal 0, which means that x can't be 10 as well. So in looking at this, we notice that we have two criteria that we have to meet as far as the x values are concerned. And so the first one is x minus 1 has to be greater than 0. Second one, x minus 10 cannot equal 0. And of course, for this first criterion, if we added 1 to both sides, we see that x has to be greater than 1. In addition to that, we see here that, of course, if we add 10 to both sides, x cannot be equal to 10. So we have to pick the x values that meet both of these conditions at the same time. And so in doing that, I'm going to draw this on a number line right quick. So here we would start at 1, 10. We know we would skip 10, but start at 1. And of course, we would have all the numbers in between there. So we're starting at 1, including 1, going all the way to 10, but skipping 10 and then going forward. So our domain here would be all values of x that are 1 or higher, but skipping 10. And that's what that would look like in interval notation. Now, for example, E, notice that it's the same function, it's just that we flip the numerator and denominator. And because of that, that's actually going to change the nature of the values of x we're allowed to plug into this function, meaning it's going to change the domain. In the numerator, we see we just have x minus 10. But since that's not in the denominator, and because it doesn't have a square root or fourth root or sixth root radical over it, there's nothing there for us to really look at, okay? So the only restriction that we have now is in the denominator. And so if you notice here in the denominator, we have square root. So there's two things that we have to consider here. Number one, we have to consider that the entire denominator itself can't equal 0. And in addition to that, we know that this radicand, which is x minus 1, has to be greater than or equal to 0. Okay. Now, in looking at this, I could go ahead and solve this equation and solve this inequality here and come up with the answer. But I'm going to try to simplify this. We know that the denominator can't be 0. So that means we know we can't plug in 1. Okay? Because, of course, if we plugged in 1 here, we're going to get something divided by a square root of 0, which is just 0. And we know we can't have 0 in the denominator. So we know having 1 being a value of x in our domain is out. Okay. We also know if we plug in any value of x that is smaller than 1, let's say we plug in 0 here, then we know that 0 minus 1 gives us a negative number, and we know we can't have square root of anything negative. So we couldn't have this situation either. So we can't have anything that is smaller than 1, and we can't have anything that's equal to 1 either, okay? So in this sense, when you say what we're saying here, a way to simplify this is the following. And I'm going to show you why what I was just talking about, how that all makes sense here. So here, to get to this x minus 1, I would need to square both sides. And if I did that, I would end up with this. And of course, if I added 1 to both sides, I would get x can't equal 1. Similarly here, if I add 1 to both sides, I get this. And so I notice here that x cannot be equal to 1, but x has to be greater than or equal to 1. And in here, we see that this means that x can either equal 1 or x has to be greater than 1. And these two things here contradict with each other. And so what it ends up being is that all we can have is the x is greater than 1 scenario. So if you remember, I had said that we have a situation where whenever we deal with the square root or fourth root or sixth root of some function here, we would have something that would be other than whatever is under the square root sign or under the radical, in the radical would be greater than or equal to 0. And this is this case. So whenever you have a function to where you have square root or fourth root of something in the denominator, in this case, you would have to say that your radicand is greater than 0, or your radicand has to be positive. Okay? So in that sense, what that tells us here is that whenever we see this, instead of writing all this stuff that we wrote here, we could have simplified everything by doing the following. And I'm going to erase this and just come up with that answer. All right, so now that we got that erased here, we know that since we have the even nth root of something in the denominator here, all we do is we have to take this and say that this has to be greater than 0. And of course, if we add 1 on both sides, that means x has to be greater than 1. And so our domain, if we write that in interval notation form, is just that. So we see just by flipping the numerator and denominator of a particular function here, we see how the domains end up being very different. All right, so for examples F and G, these will be relatively easy because if you remember here, Now we have an odd nth root. So this, we don't have to worry about the whole thing of plugging in the next value to make us divide by 0. We don't have that issue. And we don't have the issue of having a negative number in here. And yeah, that didn't turn out real well. So I'll try to draw that again. But yeah, we don't have the issue here of having a negative number on the radical here where this is even. And we don't have that because that's odd. So here, because of that, the answer is pretty simple. Our domain is all real numbers. And of course, for G, it's the same thing. The index is 3, which is odd, so that means our domain here is all real numbers as well. So these are the examples that I have, and hopefully I've done enough to kind of give you an idea about how to go look at just regular algebraic functions to figure out what their domains are and how to write them in interval notation. Thank you so much for checking out this video, and check out some of my other videos if need be. Thank you.